In the last few lectures, we had examined pressure driven flows in the potential flow limit. As I told you, the potential flow is an inviscid irrotational flow for an incompressible fluid. Inviscid implies high Reynolds number, and in that case the relationship between the pressure and the velocity is given by the Bernoulli equation. Okay. And we had looked at various examples of how to use potential flows for calculating the discharge from a tank, the metering of fluids both in a Venturi meter and in a wire, and in other applications such as rotating fluids. So, here we will be starting laminar flow in a pipe. Okay, which is driven by a pressure difference across the ends of the pipe. Okay. So, if you take a pipe, okay, a cylindrical pipe of length L, okay, and a diameter D, okay, and the radius is capital R. Okay, the radius is capital R. Okay, across which there is a difference in pressure that is applied. Okay. Across which a difference in pressure is applied across the two ends, and that generates a flow within the pipe. Okay, that generates a flow within the pipe. That generates a velocity within the pipe, and we would like to find out what is the velocity profile, okay, due to this pressure difference applied across the ends of the pipe. We will assume that use a coordinate system where x is the axial coordinate and r is the radial coordinate. Okay. R is the distance from the axis and x is the distance along the axis. X is the flow direction. Okay, there is no flow perpendicular to the x direction for a laminar flow, and we will assume that it is what is called fully developed okay. That is, there is no variation in the x direction. Okay. There is no variation in the x direction, however, it could be unsteady. Okay. So, it could be steady or unsteady. Okay. That is, there could be a variation in time, but we assume that there is no variation in the x direction. That is, the velocity at any x location depends only upon r. Okay. It is independent of the x location. That is, the velocity profile is the same at all downstream locations. Okay. The velocity profile is the same at all downstream locations. That is the assumption here. Okay. So, first we have to do a shell balance, balance over a differential volume in order to get a partial differential equation for the velocity Vx, the velocity in the x direction, and then solve that in order to get the velocity profile. Okay. So, that is what we will do. Okay. The balance condition of course is that the rate of change of momentum is equal to rate of momentum in minus plus sum of forces. Okay. And in this case we are writing it for the momentum in the x direction. Okay. So, this rate of x momentum in, x momentum out, and x forces. Okay. All these are in the x direction because momentum and force are vectors. Okay. And now we have to apply this to a differential volume. That differential volume has to be bounded by two differential surfaces which are surfaces of constant coordinate. Okay. In this case there is a variation in the velocity in the r direction. Okay. There is a radial variation in the velocity in the r direction. There is no variation in the velocity in the x direction. However, there is a variation in the pressure in the x direction. Okay. The pressure at decreases, okay, as you go from upstream to downstream, because it is the higher pressure upstream that causes the flow and which is resisted by the shear stress that is applied on the wall. Okay. Therefore, the pressure decreases as you go downstream. So, the pressure is a function of x in this case. However, the velocity is not a function of x because we have assumed that the flow is fully developed. Therefore, we have to construct a volume which has two surfaces in the r direction and two surfaces in the x direction. Okay. So, it will be an annular volume. Okay. With surfaces, okay, okay, at okay, it should be a differential volume. So, I will draw it this way. Okay. You have one surface at r. Okay. So, if I look from the direction along the axis, okay, I will have two surfaces at r and r plus delta r. Okay. I have two surfaces at r and r plus delta r. Okay. And I have two surfaces here at z and z plus delta z. Okay. And I have to write a balance equation for that. Okay. So, this is a volume that is between two surfaces at r and r plus delta r and two surfaces at z and z plus delta z along the axial direction. Okay. Okay. So, let us write here the surface areas. Okay. Okay, surface at r is equal to 2 pi r, okay, delta z. Okay. The cylindrical surface at the radius r has surface area 2 pi r times the differential length in the axial direction delta z. Okay. Surface at r plus delta r is equal to 2 pi into r plus delta r times delta z. Okay. Okay. The surface at z is going to be equal to 2 pi r delta r. Okay. That is this surface. It is going to be equal to the circumference times delta r. Okay. The surface area is going to be the circumference times delta r, and similarly the surface at z plus delta z is also the same. I should, okay, so kindly note a change in notation. I should have used x here because I have used x for the axial direction. Okay, therefore, I will use x in this case and convert all of these z's into x's. Okay. Okay. And the total volume is equal to 2 pi r delta x. Now, we have to calculate all of these terms in this expansion. Okay. Okay, rate of change of x momentum. Okay, is equal to the change in x momentum divided by time. Okay. Change in x momentum is the change in the density times the volume. Okay. So, this is equal to change in the momentum density times the volume, which is 2 pi r delta x divided by delta t. Okay. That is the rate of change of x momentum per unit time. Okay. Now, what are the forces acting at the surface and the rate of momentum in and out? Okay. The rate of momentum in okay, momentum is entering only at the surfaces at x and x plus delta x, because it is only at these surfaces that you have a velocity perpendicular to the surface that transports fluid across the surface. Okay. It is only at these two surfaces that there is a fluid velocity perpendicular to the surface which transports fluid across the surface, because the velocity is in the x direction. For the surfaces at r and r plus delta r, there is no velocity perpendicular to the surface. Okay. So, there is no transport across the surface. Okay. So, the rate of momentum in okay, is going to be equal to the momentum density into the velocity times the surface area, in this case 2 pi r delta r. Okay. Momentum density times the volumetric flow rate. Volumetric flow rate is velocity times the area. Okay. This at the location x, okay, because momentum is coming in at the location x. Okay. The velocity is perpendicular to is in the plus x direction. Therefore, momentum enters at the location x, and the rate of momentum out, okay, is equal to rho Vx momentum density times Vx times 2 pi r delta r at the location x plus delta x. Okay. See, these are the rates of momentum in and the rates of momentum out at the location x and at the location x plus delta x. Recall, we have considered a fully developed flow in which the velocity does not vary in the x direction. Okay. We have considered a fully developed flow where the velocity does not vary in the x direction. Therefore, the rate of momentum in and the rate of momentum out will be equal for this fully developed flow, and therefore, there will be no contribution to the momentum conservation condition due to the momentum entering and leaving the differential volume, because those two are identically equal for a fully developed flow. Okay. So, these terms are identically 0. Okay. What about the sum of the forces? Okay. The sum of the forces in the x direction. Okay. There are two kinds of forces that are acting. One is the pressure force and the other is the shear stress. Okay. Okay, one is the pressure force and the other is the shear stress. Okay. Pressure force acts perpendicular to the surface. Okay. The pressure force acts perpendicular to the surface. Therefore, the pressure force is compressive, acts perpendicular to the surface. Therefore, the contribution of the pressure force in the x direction acts on the surfaces at x and x plus delta x, okay, on these two surfaces. Okay. Okay. Recall that the pressure force is compressive, it always acts along the inward unit normal. Okay. Therefore, the pressure force at the location x, okay, at the surface at the location x, the pressure force is in the plus x direction. Okay. Therefore, the force at the location x, okay, it is in the plus x direction, okay, at the location x here, it is along the inward unit normal. So, it is in the plus x direction and it is equal to the pressure times the surface area, okay, the pressure at the location x times 2 pi r delta r. Okay. Force is in the plus x direction at the location x because it is along the inward direction. Okay. The force due to pressure at x plus delta x, okay, is in the minus x direction, okay, because it is acting inward to this volume. So, it is equal to minus p at x plus delta x times 2 pi r delta r. Okay. The force in the at the location x plus delta x is in the minus x direction. Okay. So, those are the pressure forces which are acting perpendicular to the surface. In addition, there is momentum transport along the momentum transport due to the shear stresses, and these shear stresses act in the direction tangential to the surface. Okay. These shear stresses act in the direction parallel to the surface. Therefore, the contribution to the x momentum equation due to the shear stress is on the surfaces at r and r plus delta r. Okay. The contribution due to the shear stress, recall that, okay, the definition, okay, tau x r is equal to force per area in x direction acting at surface with outward unit normal in r direction. Okay, that was the definition that we had used for the shear stress. Tau x r is the force per unit area in the x direction acting at a surface whose outward unit normal is in the r direction. Okay. At the surface at r plus delta r, the outward unit normal is in the r direction. Okay. The outward unit normal at the surface at r plus delta r is in the r direction. Okay. The outward unit normal at the surface at r plus delta r is in the r direction. Therefore, okay, force due to shear stress at r plus delta r, okay, at the surface at r plus delta r, the shear stress, the force due to the shear stress is going to be equal to tau x r at r plus delta r, okay, into the surface area, that is 2 pi into r plus delta r times delta x, okay, the surface area at r plus delta r, okay, the circumference times the axial distance. Okay. At the surface at r, the unit normal is in the minus r direction. Okay. At the surface at r, the outward unit normal is in the minus r direction. Okay. At the surface at r, the outward unit normal is in the minus r direction. Okay. Therefore, the force due to shear stress at r is equal to minus tau x r at r into the surface area 2 pi r delta x. Okay. So, it is in the minus x direction. Okay. Therefore, the force is minus tau x r, because if it were in the plus x direction, plus r direction, the force would be plus tau x r. Since the outward unit normal is in the minus r direction, the force is equal to minus tau x r. Okay. So, putting all these together, okay, delta of rho V x, okay, by delta t into 2 pi r delta x. Okay. Rates of momentum in and momentum out are equal. The pressure force P at x times 2 pi r delta r minus P at x plus delta x times 2 pi r delta r, okay, plus the shear stress, okay, plus tau x r at r plus delta r into 2 pi r plus into delta x minus tau x r at r 2 pi r delta x. Okay. This is the balance condition. To get the difference equation, you divide throughout by volume. Okay. In this case, for momentum transfer, you divide throughout by volume, and you will get delta of rho V x by delta t is equal to, okay, P at x minus P at x plus delta x, okay, by delta x, okay, plus, okay, I can cancel out the 2 pi's and the delta x's. Okay. So, I will get here 1 over r delta r, okay, into tau x r at r plus delta r minus tau x r, sorry, times r. Okay. I should note that we cannot cancel out the r here, okay, okay, because the surface area changes as radius changes. Okay. Therefore, I cannot just set r plus delta r and r equal. Okay. So, because the surface area changes in a cylindrical coordinate system, as the radius changes, the surface area changes. Okay. The surface area is a function of coordinate. Okay. So, therefore, I have some function which is tau x r times r at the location r plus delta r minus tau x r times r at the location r divided by delta r. Take the limit as delta r and delta t go to 0. Okay. This first term here will be equal to 1 by r partial of r tau x r by partial r. Okay. The first term is negative of partial p by partial x, because partial p by partial x will be equal to p at x plus delta x minus p at x divided by delta x. So, this is the negative of that. And the first term here will be partial of rho V x by partial t, okay, the partial derivative of the momentum density with respect to time. Okay. So, this is the momentum conservation equation for a cylindrical pipe flow for a fully developed flow where there is no variation in the velocity with the x position. Okay. And if I had a body force here, this would be an additional term f x. Okay. If I had a body force in the x direction. So, this is the momentum conservation equation. Okay. Now, we know that tau x r, okay, so we know that, okay, so we can substitute the constitutive relation for tau x r, okay, times d v x by d r. Okay. Sorry. Okay. And the balance equation becomes partial of rho v x by partial t. Okay. So, this is the momentum balance equation, okay, and if the density is a constant, I can take the density out. Okay. So, I will get rho times partial Vx by partial t. Okay. I will take the density out, and this becomes the unsteady momentum conservation equation, where Vx is a function of time and it could be a function of the radial coordinate, but for a fully developed flow Vx is independent of x. Now, this gives us an expression for the variation of pressure in the x direction. Okay. If I were to write a similar momentum conservation equation for the pressure in the r direction, I would get similar terms here. Okay. The velocity in the radial direction, the variation of pressure plus a viscous term. The time derivative of the velocity will be 0 because there is no velocity in the radial direction. Okay. There is no flow perpendicular to the axis. The flow is entirely along the axis. Okay. And similarly, there is no viscous contribution also. Okay. I should put a viscosity here. Okay. Yeah. Okay. The shear stress has a viscosity in it. So, I just put the viscosity in. So, perpendicular to the axis there is no velocity, which means that partial p by partial r has to be equal to 0. Okay. If I do a similar calculation, the direction perpendicular to the axis, the derivative of the pressure has to be 0 because there is no flow in that direction. That means that in this case the pressure is a constant across the cross section. Okay. So, we know that the pressure is independent of r, it does depend upon x. How does it depend upon x? Okay, so, let us examine that. In order to determine how the pressure depends upon x, okay, what you can do is to take the derivative of this entire equation with respect to x. Okay. If I take the derivative of this entire equation with respect to x, okay, note that x and t are independent quantities. So, I can interchange the order of differentiation. X and r also independent quantities, they are independent coordinates perpendicular to each other. Therefore, I can interchange the order of differentiation for x and r as well. Okay. So, if I do that, take the derivative and interchange the order of differentiation, I will get rho times partial by partial t of partial Vx by partial x is equal to minus partial square p by partial x square plus 1 by r Okay. I differentiate with respect to x and interchange the order of differentiation, okay, and this is what I get. And since it is a fully developed flow, there is no variation of the velocity in the x direction, which means that this is equal to 0 and this is equal to 0. Okay. So, both the left and the right sides are both equal to 0. Therefore, I get d square by partial x square is equal to 0, which means that partial p by partial x is equal to a constant. Okay. Therefore, the pressure is a linear function of x. It decreases linearly as you go downstream, okay, for a fully developed flow. Okay. Therefore, the pressure gradient is a constant. It is independent of x, okay, in this particular flow. Okay. And since the pressure gradient is a constant, we can now integrate this in order to find out what is the velocity profile. So, this is the balance equation that I have got for you. Okay. There could be an additional body force in the end over there. Okay. We will discuss that in the next lecture. This is the balance equation. The radial derivative of the pressure is 0. And the pressure gradient itself is a constant for a fully developed flow. Okay. When I say a constant, okay, dP by dx is a constant, but if the pressure was a function of time, dP by dx could be a function of time, but it is independent of position, okay, for for unsteady flows, okay, dP by dx could be a function of time, okay, but it is independent of x, okay, and unsteady I should mention here fully developed. Okay. For unsteady fully developed flows, this could be a function of time, but it is independent of x. Okay. So the derivative with respect to x is independent of x. So it is always a linear profile. That linear profile, the slope could change with time, okay, depending upon the values of pressure at the two ends. So I will review this derivation in the next lecture before I go on to calculating the velocity profile for the flow in a pipe, and then the friction factor correlation for the pipe flow, for a laminar pipe flow. Okay. So I will continue this in the next lecture. I will see you then.